Well, it's a great pleasure to introduce our colloquium speaker for today, Sir Simon Donaldson from the Imperial College London and Stony Brook. And he'll be talking about integral curvature bounds and singularity formation.
This invitation. Let me just say at the beginning, I'm aware this is a colloquium talk. Normally, most often in colloquium talks, one tries to give a broad overview of some area, not go into any details. I'm going to take a rather different model today. That I'm going to talk about a specific, maybe even somewhat technical result. Give rather a minimal amount of background in the first few minutes, but I do hope to try to not give the proof, but at least convey to you the main ideas of the proof, because it's of a relatively elementary kind, I think, which I hope that may be possible. But we'll see whether that's, at the end of the hour, we'll see whether this is good or not. So, what I'm going to talk about is some joint work with Chen. And everything I would say is in a paper on the archive. Here. And just to say, to talk briefly about the background, we're interested in, we have a sequence of Riemannian manifolds, of X dimension n, and supposing these have a limit, it's not talking in a technical sense at the moment, which is some kind of singular space, instead, we're interested in understanding what kind of singularities that can arise in Z. And today we're going to discuss this question under the assumption that we have some integral bounds on the curvature of these manifolds. So we take this usual LP norm of the curvature tensor of our manifold. Various values of P. There'll be various other more sort of technical things we should say. In fact, we're going to be supposing we're in a context where the Ricci curvature of our metrics is bounded, and in fact the simplicity, just a statements. Simpler, let's suppose in fact these are Einstein manifolds and Ricci to zero. But this is, in fact, this is not really going to enter in any explicit way in the talk. It's just, we need to have some hypothesis like this to make the statements correct. So there's a general theory about Cheeger and holding about these singularities, these kind of spaces. In particular, they have the theory of tangent cones. Which so we consider tangent cones to be of the form of a cone over some space y times some flat directions. So it's n. N is the dimension. Let's consider n is the number of flat directions we split off in our tangent vector. And let's write k for the dimension of this complementary. So k. So if you just think about this this cone, then the let's suppose momentarily that y is smooth manifold, then the curvature distance, the vertex, the cone, then this will just be some function of y over r squared. It will grow just from the scaling properties, it will grow like r squared, r to minus 2 as we approach the vertex.
Little y is an element of capital Y.
It's yes, y. So if this, supposing this function is not identically 0, then we can understand that in this tangent cone, how these integrals behave, we'll be looking at the integral up to this. Here, in the radial direction, we're looking at 1 over r squared p times the volume element will be like r to the k minus 1 r. And this is finite if 2p is less than 3. So we just want to understand the behavior of the LP, normal to curvature, of these cones in terms of relation between this dimension k and the exponent p. So the essential case, from our point of view of interest, is when this function f is actually 0, so that the cone, the curvature is actually 0. And again, let's go straight to the essential case, is when y is a smooth manifold, and then what this amounts to is saying that y is the quotient of a sphere by the action of a finite group. So this gamma is going to be a finite subgroup of S actually freely on the sphere, so we can make this example left bound. This implies that k will have to be even if the simplest case would be when gamma is just a group of order 2, acting by multiplication by plus or minus 1, and then this thing will just be a real projective space. Questions? So this is our base of our cone, y. The actual cone then will be just the quotient of r to the k. So such things, these flat tangent cones do arise very often. For example, it has to be take a Kuller surface. This surface refers to two complex dimensions, but from our real point of view, we take a four-dimensional torus and divide by the action of the group of order 2, and then we'll have 16 singular points of this model on this curve. it's well understood that you can deform this singular space to a non-singular one, or a family of non-singular ones. If we replace this cone essentially by what's called a Higuchi-Hansen space, we have a one-parameter family of genuine smooth manifolds approaching this singular limit, where so near the cone point, before we go to the limit, we have a two-step non-zero homology class which tricks down to a point as we go to the limit. And there are many, in the work of Dominic Joyce, for example, there are many more important examples where one takes a seven-dimensional torus and takes the quotient by some G and get singularities of these models. So this is the end of the background. Really. We probably want to move on and say now, supposing we have one of these flat limiting spaces, we don't see any curvature in the limit. Do we still need, how much curvature do we need in order to produce such a singularity? That's the basic question we want to study. So, the case when k is 2 is different, so let's restrict attention to the case when k is bigger than 2. And so we're going to consider our model space, which is r to the k of gamma times Rn. And let's write, say, b gamma to be the unit ball. In the obvious sense, taking the origin, the obvious meaning of what you mean by the origin in this space. So, schematically, we could draw a picture as though M is 1. Picture our space, so around here, we actually have an sk minus 1 over that. Around here, we are our ball center. So that is just the quotient of the unit ball in R n plus k by the action of gamma acting on one factor. So let's state the main theorem we want to discuss. So we consider a unit ball in one of our manifolds N. So under our, it's supposed to be a manifold in zero reaching curvature for simplicity. So it says there are two numbers. Gamma, such that I'll explain this in a second, if the distance between B and B gamma is less than the delta, then the integral over B of the L k over 2 form of the curvature tensor is at least alpha. say.
B is a smooth thing, right?
This is a smooth environment. It's a ball, you know. It might well be a very tiny ball, the manifold you first thought of, but then we can scale up to it.
So you can't smooth off the singularity without introducing a lot of curvature.
So we can say, in the very course, we can't smooth off without making curvature. Definite amount of curvature, in a sense, or saying another way, you can't develop this kind of singularity without having a definite contribution from the curvature in this sense. So the main case of interest, where K is 4, so this is the L2 norm of the curvature tensor, and there are situations in which one does, from the natural hypotheses, have some control of the L2 norm of the curvature tensor. And then what we're saying is that to produce a bit of codimension for singularity, we need to use up a definite amount of that L2 norm that we have. But that translates into getting some control about the size of this codimension for singular set. Like I said, I'm not going to try to go into the background applications of this more, apart from trying to convince you it's a useful thing to know from the study of these limits, for instance. What I haven't explained is what we mean by the distance between our model ball, P gamma, in the singular space, and this smooth Riemannian ball. What I mean here is what's called the Gromov-Hausdorff distance. But we don't actually need to say what that is, because under our hypotheses there's a much more explicit way of saying what this means. Let's introduce another set inside our ball, where we, depending upon the parameter eta, where we remove a tube around the singular set. There's the distance eta, and so we get a set with u eta. The subset of this model ball where we just drilled out a tube around the singular set, size eta. So saying that the ball, the other hypothesis that this ball is close to the model is the same as saying that there exists some for some eta, depending upon delta, there is a map pi from its u eta to our ball, so that if we compare on the image of this map, if we compare our metric that we have on the manifold with the model metric, there's the difference is arbitrarily small in any standard norm. So the norm, we get G naught being the model metric on this space minus pullback G. So that's the eta with any norm we want to put, and then over the eta. This is our ball P. We map u eta. We map this thing here. So we have a region which we essentially completely understand. It's essentially isometric to this drilled out set u eta. We're going to have some. This is not the whole of P. There's some unknown region in here, corresponding roughly to the singular set. We're not going to say anything about that, except to say that any point in this unknown region is within a distance, we say 2 eta, I think we should say, of a point in the image of our known region. So we don't know what's happening here. We know that any point in this unknown region is close to a point here. So the pi of u eta is 2 eta. And this is equivalent with a suitable translation of the parameters between eta and delta. This is, it turns out, equivalent using difficult theorems, including the theorem of Michael Anderson. This is equivalent to saying that they've gone off Hausdorff close to this form. But essentially, you could think of, without really losing anything, you could think of saying that the metric here is identical to the metric on U eta, but rather than having a singularity, we're filling in with some unknown thing in the middle. All we know is that it's any point in here is close to a point. So let's just say that when K is the case for K is 2 is special, but there is a similar statement, or perhaps a very stronger statement, to do Cheeger. Which I may mention again, possibly. Right, so this is, I've said, the whole rest of the talk is going to be about this maybe somewhat technical looking theorem of Riemannian geometry. I've tried to explain the significance of some part of it. Are there any questions about before we press on? Anything I can say to explain this properly?
About these change points, is that like a very generic phenomenon or the most interesting phenomenon, or as a limit, the kinds of singular limits you can get? Why are you setting these limits?
Well, because for the other, as I tried to indicate, if you had a cone on Y which is not flat, then you'd know that needed a depth amount of curvature, just from this calculation.
Why it's not cones in general?
You mean Y cones in general?
Yeah, what?
Oh, that's a deep part of the Cheeger-Colvin theory, that you have tangent cones which always have this shape, and then from the definition of the tangent cone essentially means that you will have a ball that's close to the ball. But you can think about these explicit examples when you see their explicit examples. So this in most cases, to say for most possible groups gamma acting freely on the sphere, this theorem is known, or was proved by Cheeger, Colloquium, and Chern about 10 years ago. In particular, for the gamma which arises in the case of Taylor manifolds, particularly the fourth case, all covered by this 2002, published in 2002. So let me spend a few minutes trying to give an idea of the Cheeger, Colloquium, and Chern proof, and why there's difficulty for why some gamma are less tractable than others. Let's momentarily think about the case, the two-dimensional case. So we're just thinking about a two-dimensional manifold. Supposing it's actually equal to a cone outside a certain region, isometric to the cone. So if we take our cone, which the parameter alpha, so we take the unit distance of the cone, rather than being 2 pi, let's say this circumference is now 2 pi minus alpha, so theta. Then, so we're supposing this manifold is isometric, so for this one, color region as indicated. Then, a version of the Gauss-Bonnet theorem says we take the integral of the curvature, which now reduces to the Gauss curvature, over this manifold, will be given by the formula theta minus 4 pi g, where g is an integer of the number of angles we have inside. So we can say up to essentially integers, we normalize the integral of the curvature depends only on the boundary. So this is the simplest instance of the general called the Chern-Simons invariant. In general, so let's suppose we go on to our problem in which this number n is 0. So we're just considering extra product factors. The analog of looking at the integral of the Gauss curvature in higher directions is to take a certain polynomial, Pontryagin polynomial of the curvature, integrating over our ball B. And the analog of this formula is to say that this integral is equal to an invariant of the boundary of B, the Chern-Simons of the boundary of B, modulo Z. We normalize out to 4 pi's. And this, under our hypothesis, the boundary of B is very close to the boundary of, so this is essentially equal to the Chern-Simons invariant of this sk minus 1. We'll have the modulus, this is a polynomial of degree k over 2, sorry, 2k, so, what's it right? So, well, k is k over 4. So we keep it in 4 dimensions, so we can consider it P1. This is a polynomial direction k over 2 in the Riemann curvature tensor, so this thing is certainly controlled by the integral of relevant power terms. So in the case when there are no product factors, we'll just have this simple situation. If we know that this Chern-Simons invariant is non-zero, it's something that takes values in R modulo Z, then we know that this integral of the Pontryagin class is non-zero, and therefore we know that we get a bound on the integral of the appropriate integral. Okay. So here I'm the central case is where k is by 4. So the problem, the reason why we say most gamma is that we take most gamma, indeed this thing will be non-zero, but there are cases, I'm told, reading cases of Cheeger, I know, but there are cases where this Chern-Simons invariant is 0, so it's sort of visible from the point of view of this argument. We don't see the difference between this and the sphere from the point of view of this argument. But let's suppose, let's leave that aside, let's carry on with considering, supposing in the case of a good gamma, in which we do have this non-zero Chern-Simons invariant. The case n equals 0 is straightforward, as we indicated. How about the general case? So we do have some extra factors. What Cheeger, Colloquium, and Tian do is to construct a slicing function with F to the map from our ball and our manifold to Rn, which on this known region is essentially corresponds to the projection here onto Rn. So it's a map that does essentially does the obvious thing on the known region, but is extended over the unknown region in some way. So roughly speaking, we look at the fibers of this map, and this will be some generic parameter values. Z is the parameter value here. We look at the fiber, F minus Z, and this will be a manifold. And the argument is to, roughly speaking, apply this argument on the fibers of this map, and then integrate over Z. But that requires a lot of hard work in controlling the second fundamental form of these fibers. In fact, we can't do that for all Z, but in a suitable sense for almost all, for most Z. Control the second fundamental form, and then do this argument in this tab, roughly speaking. So let's now complete the background. What we want to do is to give a proof which has interest because it's different from Cheeger, Colloquium, and Tian, and in a sense more elementary. We don't just merely show Simon's identical stuff. But also has the advantage that it fills in a sort of lacuna in the theory about these exceptional gaps where this argument breaks down. The goal is to give a different proof.
Does this proof work for all even K or just K multiple of 4?
The proof we're going to give.
You just sketched a Cheeger holding down.
Yes, I forget. Something I hadn't thought through why we can reduce, whether or why we can reduce to multiples of 4. The same thing, let's suppose we're multiples of 4. Yes.
Why is this so lower bound? I mean, the periodic process put something like R with R, right? It's just something is it like a non-generic polynomial or something, or what's?
Let's take K to be 4.
Yeah.
This is P1. This is a quadratic polynomial in the curvature.
And it controls
which is controlled by the L2 law of the curvature. So with some.
Oh, sorry. I got the.
So we can halfway through we can begin.
See for the Tian pattern is for color before.
K multiple of 4?
Yeah, K.
But specifically, curvature for K is.
Yeah, that is.
So a crucial idea we want to think about, very crucial but very simple, is staining. I'm going to say something completely obvious. If I have some ball in a random manifold, okay, center P radius R, let's just write B sharp. We're just the same ball, but we rescale distances by a factor R to the minus 1. So this is our unit ball. Trivial, of course, we can always translate anything we say about there to there, I suppose. But it's an important way of thinking. So let's go back to the picture we had, just to take an example. Say, for example, our asymptotic, our two-dimensional manifold, say asymptotic to the curves. We take a P here. And let's think about what would these balls be when we reach scale. But don't think are very large. Maybe it's not, say, 100, it's a large number. Now this is going to be essentially a cone. Because everything here is going to be shrunk back into the point. What we're going to see is the large cell structure of this cone. So it's going to look pretty much like this. If I take intermediate value, okay, 1, then I'm going to see some interesting curvature and topology and things happen. So, whereas if I go to a tiny value, sufficiently tiny, then I'm going to see essentially a flex. And the definition of a Riemannian manifold, we take a sufficiently tiny ball, and scale it to unit size, and it looks essentially like the standard thing. So as our radius moves through this range, we move through these three pictures. Just an example, we can do many other things. But this is what I want to think about if I follow the proof of the electron outline. Similarly, let's introduce the normalized energy. Right, so this is going to be 1 over r to the n minus k times the integral over the ball of radius r centered at the point P of this power that we're considering of the curvature. So this is just the same as taking this factor just takes account of the scale. So it's the same as to take the rescaled ball and then just take this. This is what we want to see. And this is a very well-known thing in the Riemannian geometry of a PDE thing. So you take an energy function with a scaled version of this kind of lines. But then, what will take definition? Let's define A epsilon. If you're given some parameter epsilon, this is going to be set of P in our ball we're studying, such that this energy, this normalized energy, is less than epsilon for all r. So for all balls centered at this point, the energy is always in this sense, it's always very small. So you take this point, you take any ball scaled to unit size, we're always going to see a very small LK over 2 norm of the curvature. That's the definition of this thing. So let's go back to my picture. So we'll define a set X. Let's not give a definition, but it corresponds to a set like this. It's easy to define a set with X like this. So it corresponds to a standard sort of slab in this picture, and then we take all points into a certain distance. And so this thing will have two kinds of boundary components, an outer boundary here, and another boundary here. That means we've got the outer boundary. Let's call that, say, boundary naught. Outer equatorial region. So the crucial proposition we want to prove is a topological statement about this this set A epsilon, or precisely the part of A epsilon that lives inside S. So the proposition, time is running on the side of the circuit. This is epsilon is going to be a sufficiently small number that we're going to fix at a later stage. there exists a retraction, a continuous map R from S intersect X island. So, something I forgot to say. Without loss of generality, we can suppose that this boundary region lies inside AX island. Because essentially the manifold's flat out there, so you can see. So what we have to say is a retraction from the product A inside the central slice onto the boundary and in that continuous map such that R is the identity. This is a topological statement. All we would say is this is a continuous. I'm not saying anything about geometry. So the two things to do. One is to say, why does this topological proposition imply the theorem? And then why is this topological proposition true? 30 minutes. So the first is more standard. So let's do that. We're going to use a similar idea to achieve Colloquium and Chern, but in a much more primitive form. I'm going to have these slicing functions. So we have all we need to know is just this is an elliptic slicing function. So the derivative of x is less than 2, say. So this is going to be a function which is essentially on our essentially flat region is essentially given by the projection to the Rm factor under our math pi, but we extend it in some way as a Lipschitz function over the complicated set. And this is easy to achieve without any of the difficulties of these technical form things, just using the distance function. If n is 1, you just take a point. So reduce the case when you're on a much larger ball, which is you take a point a long way away, you take the distance to this point. So this is not at all difficult to construct. Now let's look at the fibers of this map, so as we did before. And so it's not really necessary, but for simplicity, let's work at almost all points said, in which the fiber will be a smooth map. Because this map is actually smooth, but we only have control of the derivative. We're not saying control. So this is going to be a manifold with boundaries, if you have something going. At least if Z is constrained to a suitable region corresponding to this set S, which is, say Z is this on halves. In fact, the boundary, what's the boundary going to be, is essentially going to be the same as the model case, where this is just a projection map. The boundary is going to be is diffeomorphic to this SK and so on. But we can. So it's a compact manifold boundary. We can arrange that we don't get off this right into this part of the boundary. So this is the one of the key things to convey. If nz were contained in A epsilon, then what would we have? Our map R would give a retraction of nz onto its boundary. But that's not possible. You can never take a manifold with boundary and retract it onto its boundary by the basic lemma in first year homology theory. But if we look at R of nz boundary set, retraction, so that's impossible by homology theory. So this is not the case. So each fiber must meet a point not in A epsilon. So we use. So we use that proposition, so we can run it out now. And the remaining thing is just a simple covering argument. Let's speak covering argument. It's hardly hammer, it's called a variant of that, but we can find disjoint balls so di with radian Ri such that the twice-size balls cover the complement of A epsilon, and the energy of these balls, so let's say center Pi, so an E of Pi is bigger than this. This just follows from the definition of this thing. So at each point of the complement, by definition, if it is in the complement, by definition, we've got some radius where this energy is bigger than epsilon, but we're going to define epsilon, and then the simple covering argument says that you can find the counter collection of balls of this kind. But now we know that for each Z, or each Z in this inside the half ball in this case, the fiber over Z meets the complement of epsilon. This doesn't lie inside epsilon. So that's what's saying is that the union of f of Bi, 2Bi, covers the half-size ball in our parameter space. Yeah. In each Z, in this range, we have some point not in epsilon hits it. That point not in epsilon is inside one of these twice-size balls, so that's the same. This is the Lipschitz map, so the radius, the image of this twice-size ball is not too big. In fact, it's contained in a ball of radius 4 times Ri, in our Lipschitz quantities. So, what we get is that the sum of ignoring factors, the sum of Ri to n is bigger than some computable constant, non-zero constant. Just using the fact that the image of these balls must cover this definite size emulation on the set. On the other hand, because these balls are disjoint, the integral over B of the estimate of this thing, this is certainly bigger than the sum of the integral over Pi's. But that's just given by that we know about this, but by a definition of our energy function of E. This is bigger than or equal to epsilon times the sum of R to the n minus k. And the way to define what we mean by this. And this is the same F. So, together, we've done what we want. Well, it's covering our, we've achieved what we want to do. So that's halfway there. We've gone from this very topological statement about this set A epsilon, the set where in all scales you don't see curvature. It's allocated into sense to the estimate we wanted to prove. Using some very elementary homology theory and this elementary analysis of covering. So, should I say anything more about this? Pressing on to the last answer.
So if you show this walls BI, how is it in this space?
Suppose that we said that all of this set is an epsilon. So A epsilon might be some set like this, imagine it. And these are balls that essentially are covering the complements. So these are balls here, which are forced to see them. That would be kind of picture. Okay, so the last 10 minutes is how to prove the.
So these are by definition distance balls, and you don't know that they're topological balls.
They're all only distance balls. And I haven't said, it's true, I'm not hypothetically considering the volumes of balls or these are. So these are just Riemannian balls. So the last 10 minutes we need to discuss how to prove this proposition. This topological proposition. I've given this talk before, or a similar one, with the subtitle Toy Story 4. It doesn't really explore Riemannian geometry. Not sure. I do have. I possibly wouldn't. And I'm not sure how much I'll be able to bring them into the exposition, given the short time delay. So let me try to. I mean, this is not completely a trick. Let's see. So the key thing is the rigidity of Rn times. This is a Stony. So I mean rigidity among flat singular spaces. You can't take this space and deform it to some other kind of thing without seeing some curvature. That's what I can do. Of course, I can see more precise. This is what's different in the case of k equals 2, because you could take a pair of, you could take a single singular point and split it up into a pair of singular points in dimension 2. So that would be essentially different. But in this case, it's pretty intuitive. You can't, this is essentially saying that you can't deform a finite group. This is a thing where the representation of gamma, you only deform that object by convex, and you only can't essentially change it. So, to explain how that's done, I like to say, I actually did it in terms of an astronaut, let's call him right here. That's, but if flying through space, he sees far off this singularity in space. So what he sees from far off essentially is the model. He keeps on going, and he's always going to stay inside the set A epsilon. So he's never allowed to see any curvature, any scale in the sense. Then, so basically he's going to examine, wherever he is, he's going to examine things on a scale up in the distance to the singular set. Now, the thing is, he can never see any different picture. He starts off seeing this thing, keeps on going. He's never allowed to see any curvature. So all he can see is some kind of singular thing, but the singular thing is rigid. So he's always going to see the same picture. But you never get to the singular set. You never. And therefore, that's why the whole A side would be refracted back into the moon. So you can never go, in terms of our pictures that we have these pictures. He starts off like that. He's never allowed to go through this, because then he's staying inside A epsilon, because then he sees some curvature. So you can never get to that. So that's the argument. And of course the proof is quite different. The proof requires some substantial work. This is the basic idea. Eventually you'll buzz Lightyear. That's the argument for the half yarn. That's the Buzz Lightyear part of the argument. So what you see is that I'm also say this in a slightly more precise way. Supposing we have a point. Not exactly equivalent to what I'm trying to indicate. Supposing we have a point inside A epsilon. That's supposing it's a point. The interesting case is when it's a point in this potentially singular region, or close to singular region. Then, at all scales, if we take any radius r, normalize our ball, this is essentially isometric to a unit ball in the homomorphic sense. This symbol is essentially isometric up to a small level. So so we start off here at scale 1, so a picture of our model here. So let's say center. When r is roughly 1, Q of r is going to be the origin. But eventually, because it's a smooth manifold, Q of r has got to move away from the singular set. So Q of 1, so here, for r, Q of 10 to the minus 7, I think it must be out here, because we're in a smooth manifold, so it's a tiny point, this thing must look like a, can't look like that, it's got to look like a, so for some very small number, you don't know anything about, depending on P, but there is some number which, when we take this model ball, the center has moved away from the singular set. So what we need is an escape strategy. So we're trying to construct our retraction map, but we're thinking that's a way of getting from our point in A epsilon. We've got to find some way of escaping from the singular set and getting out to this outer boundary. That's what we want to do. Well, this is the woody part. What we're going to do is we're going to lasso the singularity to construct our escape strategy. What do I mean by that? When we define a lasso, time is running out, so I'll just have to say, I don't know anything about It's a configuration, so it's centered at some point x. It consists of a geodesic, the gamma naught, and a geodesic loop, like this. And we'll define a weighted length function to be the length of gamma naught plus k times the length of gamma 1, where k is some large parameter that we're going to choose. And this will depend upon the group gamma. It is some large number. Then we can define a function, f of x, over all lassos starting at x, as it were. Then we look at this length function, we can minimize the length. These are definitions we can write down in any Riemannian manifold, more or less, by this case. And then we can find a vector field, V, is the gradient of x. There's some technicalities that actually this might not be, from the definition, might not be a smooth function, but it's Lipschitz, and you can smooth it out and everything. The technicalities don't actually matter. So in particular, we can do that in our situation. To define some vector field over our ball. So when our point is escaped from the singular set, what's going to happen? Essentially, the minimal lasso must be something that goes around, or does something. There's some small geodesic loop inside the complicated part, and it's more or less the standard straight geodesic. So here, the vector field is the standard kind of gradient vector field up to a small range. So starting from this picture, after we, at a scale where our points escape from the singular set, we just follow the gradient. We iterate this vector field, follow the gradient, and we essentially escape to twice the distance out. So now we can go to a picture of twice the scale, and now we're distance half out. We have the same picture. We follow the gradient field, and we get twice the distance out, and we keep on doing it. We do it carefully. We don't think we build up the errors. We can keep on doing it as many times as we like. It doesn't matter if it's 10 to the minus 7 or any number. You keep on seeing the same picture at each scale, and eventually you escape to the boundary of your ball. That's how you construct this. Is your escape strategy from getting out of the singular set, out to the boundary, and defining your refraction. Whereas, in terms of really, what you do is you assume the singularity. Lean back, follow the gradient, and you just keep walking. To find a consistent way of getting out, provided you started inside and outside. So you're not going to see any difference from basically the standard model that you say. You get a consistent way of escaping and construct this retraction. Okay.
In this definition, is the geodesic loop gamma 1 allowed to be in principle any geodesic loop, or is it specifically supposed to represent?
No, any non-trivial geodesic loop. So on the very general hypothesis, this is a well-defined loop. As long as it's a non-empty set of such things, this is the main kind of function.
So if you were in a complete Riemannian manifold, it would be less difficulty proving the existence of such a loop.
Well, in this case, you only care about
What's going on?
particular points. So there's some small geodesic loop inside this nearly singular piece. In the context you're working, there's no you could set up a general.